Assalamu alaikum, dear student. Welcome to Nuclear Physics Lectures. In today's lecture, we will talk about single stage accelerators. I'm Dr. Pervaiz Ahmad. The working principle of the single stage accelerator is basically that we have the total potential produced from high voltage generators as imposed between the ion source and the target, and then the kinetic energy of the particle is equal to nqv. I mean, this is the sample working principle of the single stage accelerators. That is, let me repeat it again. We have the total potential produced from high voltage generator, and that potential that potential is basically being imposed between the ion source and the target. So what actually we achieve with this, we achieve a kinetic energy of the particle. I mean, we accelerate the particle, and the kinetic energy of the particle which we accelerate is equal to nqv. Here n basically mean the number of stages, which here in this particular condition is equal to 1. Q is the charge of the accelerated ion, and v is the potential across the acceleration gap. Single stage accelerators, which recently been employed, consist of small version of the Kakarov Watson accelerators and transformer rectified accelerators. I mean, these are the two basic kinds of the accelerator which has been used for acceleration of the electron or acceleration of the deuterons for the productions of the neutrons. What actually we have, just like you can see it here, and this particular reactions, that is tritium targets are bombarded by accelerated deuterons. So as a result of that, turning of the Coulomb barriers results and good yields for this reaction, even for zero point 0.1 mega electrons volt. What actually happened, here you can see the sketch of the single state accelerator, and here you see that we have notifies all the thing which is happening inside this particular accelerator. So what actually we have deuterium gas here, that is the D2 molecules. D2 basically stand for the deuterium gas molecule. So what actually happened with the D2 molecules? The D2 molecule leaks through a heated palladium foil into the vacuum of the ion source. I mean, this is the vacuum of the ion source. So the D2 gas molecule leak here to a heated palladium foil and to the vacuum of the ion source. This is the vacuum of the ion source. So what happened after this? You can see it here. Here we say that there are high frequency electric field So what actually we do with the high frequency electric field? So the high frequency electric field decompose the deuterium molecules to form the deuterium ions and the electrons. I mean, first we carried the deuterium gas here to the ion source, the vacuum of the ion source, and then we apply high frequency electric field. So this high frequency electric field is basically decompose the deuterium molecules to form deuterium ions and electrons. So after that, what happens? These ions are extracted with the negative potentials. I mean, we extracted here from this particular locations, extracted with the negative potential to enter the acceleration tube. I mean, here, this is the acceleration tube. I mean, the ions which are being produced here, this particular location, they are being extracted with low negative potential to enter the accelerated tube with a kinetic energy equal to 2.5 kilo electron volt. So after that, what happened? Uh, here we have 100 kilowatt. The 100 kilowatt is obtained from a transformer and rectifier unit coupled to a set of cylindrical electrode connected by a resistor chain. I mean, here you can see what we have. I mean, this is 100 kilovolt 100 kilovolt in this 100 kilovolt, I mean, it's a voltage. 100 kilovolt voltage is obtained from a transformer and a rectifier unit. I mean, here you can see the rectifier unit, and they are being coupled to a set of the cylindrical electrode connected by a resistor chain. So what actually we do, the the beam a particle exit the last electrode. I mean, here you see we have the concentric electrode. These are the concentric electrode. So the beam particle exit the last electrode. I mean, this is the last electrode, um, and trapped through a short tube. This is the area. This is the short tube. This is the ratchet tube. So what happened then? uh, and strike the target. I mean, here you can see this is the target. The beam particle exit the last electrode and drive to a short tube and strike the target. So what is the target? The target is basically titanium with the observed tritium. I mean, this target is basically titanium with the observed tritium. So what happened then, the target, I mean, here you can see that we have some cooling process for the at this particular location. So what is this cooling? We have cooling water, and this cooling water basically used for the target. What it mean that the target is being cooled by water. And what is the purpose of this cooling? The purpose of this cooling is to minimize tritium evaporation. I mean, sometime I mean, tritium evaporate if the target is too hot, I become too hot. So in order to avoid this, we have a cooling process here. We utilize cool water. Here with the target, and the basic purpose of this is to minimize tritium evaporations. So with 100 kilovolt kilo electron volt and 0.5 milliampere, the accelerator can produce 10 raised to power 10 stages per second with 14 mega electron volt. I mean, this is the thing we can achieve with this particular energy, with this particular kinetic energy, and this amount of the current. So it can reduce kinetic energy to thermal value, and the thermal value, you know, that is equal to 0.025 electron volt by placing water or paraffin around the target. I mean, if we place here, around the target, we place water or paraffin, so we can reduce the kinetic energy to that of the thermal value. The thermal value is 0.25 electron volt, and that can simply be done by placing the waters or paraffin around the target. So flux of the thermal neutron will be equal to 10 raised to power 8 stages per centimeter square. So production rate of the neutron increases. What do we have? Production rate of the neutron increases as the beam energy and beam current increases. I mean, here this is basically the beam energy and the beam current. I mean, we have at the start, at a particular point, we have the beam energy 100 kilo electron volt and the beam current 0.5 milliampere. So here we say that the production rate of the neutron increases as the beam energy and the beam current increases. What it mean? It mean that if we increase this energy, this kinetic energy, which is 100 kilo electron volt, and this is the beam current 0.5 milliampere. I mean, if we increase these values, so the production rate of the neutron will also increase. So this is all we have for single stage accelerator. So see you with the next lecture.